refinery produces gasoline utilizing the principles of fractional distillation to separate the gasoline from the crude oil mixture. Crude oil is heated by a furnace to a temperature between 320 and 370 degrees centigrade, and then pumped at a constant rate into the bottom of a tall fractionating column. The fractionating column is separated into 30 or 40 perforated fractionating plates spaced at regular intervals. Once the crude oil is in the column, its components separate based on their boiling points. The butanes, pentanes, and hexanes have lower boiling points, so they move up the column where they can be removed by condensation near the top of the column. As these substances separate, they leave other components such as toluene and benzene. These components have higher boiling points and are less volatile, so they remain near the base of the column. From there, they are removed as liquids. Part of the liquid condensed at the top of the column, called the reflux, is pumped back into the top of the column and runs down from plate to plate to maintain the equilibrium in the column. The use of reflux and a column with plates distinguishes fractional distillation from simple distillation. Whenever there are two or more components of a liquid mixture, such as pentane, with a boiling point of 36 degrees centigrade, and hexane, with a boiling point of 69 degrees centigrade, fractional distillation can be considered as a process for their separation. In this process, the individual volatile components of a mixture are distilled and collected one at a time. In order to discuss the theoretical basis for fractional distillation, it is helpful to first consider the behavior of a one-component system. In any liquid, such as pentane for example, some of the molecules have enough energy to overcome intermolecular attractions and leave the surface of the liquid, so that part of the liquid vaporizes. As this process occurs, the pressure exerted by the gas molecules rises. In a closed container, some of the molecules which have left the surface may eventually strike the liquid surface again and not be able to leave. These molecules have condensed. When the rate at which the pentane vaporizes equals the rate at which it condenses, the system is at equilibrium. The pressure under these conditions is called the vapor pressure. If the temperature of the pentane is raised, its vapor pressure rises. A graph can be constructed by plotting the vapor pressure versus the temperature. For a pure liquid, such as pentane, there will be a temperature at which the vapor pressure equals the normal atmospheric pressure of 760 torr. This temperature is called the normal boiling point. Pentane has a normal boiling point of about 36 degrees centigrade, which is slightly below human body temperature. When hexane, represented here in red, is mixed with the pentane, the mixture of the two liquids forms an ideal solution. The total vapor pressure of this solution is equal to the sum of the partial pressures of the individual components. The partial pressure is proportional to the mole fraction of the component in the mixture. This is Raoult's law. Consider a mixture at room temperature that is 50 mole percent pentane and 50 mole percent hexane. If the sample were pure pentane, the pressure of pentane above the liquid would be about 400 torr. Because it is only 50 mole percent pentane, the partial pressure exerted by the pentane is only 1/2 of 400 torr, or 200 torr. In a similar manner, if the sample were pure hexane, the pressure of hexane above the liquid would be about 112 torr. Because it is 50 mole percent hexane, the partial pressure exerted by the hexane is 1/2 of 112 torr, or 56 torr. The total pressure above the mixture of pentane and hexane is equal to the pressure exerted by the pentane, 200 torr, plus the pressure exerted by the hexane, 56 torr, or about 256 torr. The lower boiling component, pentane, contributes more to the total vapor pressure than the higher boiling component, hexane. If the vapor over the solution were removed, condensed, and then analyzed, it would be found that the mole percent of the lower boiling component, pentane, was higher than it was in the original 50-50 liquid mixture. That is, the condensate would be richer in the lower boiling component. Specifically, in this case, the condensate would have a mole ratio of about 200 to 56, or about 3.6 times as much pentane as hexane. This ratio reflects the ratio of the partial pressures above the original 50-50 liquid mixture. At the boiling point of mixtures of liquids, the compositions of the vapor of the liquid are often displayed as boiling point diagrams, sometimes called liquid-vapor composition curves. On these diagrams, the vertical axis represents the temperature, and the horizontal axis represents the composition of both the liquid and vapor states. This diagram is for a mixture of hexane, which has a normal boiling point of 69 degrees, and pentane, which has a normal boiling point of 36 degrees. The bottom line is the equilibrium temperature composition curve for the liquid. The upper line is the temperature composition curve for the vapor. As an example, examine what happens if the 50-50 mixture of pentane and hexane is heated. The initial normal boiling point is about 45 degrees. The mole percent of pentane in the vapor is determined from the tie line on the graph between the liquid and vapor equilibrium phases. In this case, the mole percent of the pentane in the vapor is about 90%. If the vapor phase is removed and condensed into a liquid, a process represented by the vertical line on the diagram, the liquid obtained is still 90 mole percent pentane. If this condensed liquid is heated, it will boil at about 37 degrees, and the mole percent of pentane in the vapor phase is about 98%. Repeated vaporizations and condensations eventually lead to the collection of pure pentane, the lower boiling component. Each cycle of vaporization followed by condensation on a boiling point diagram is known as a theoretical plate. Actual fractionating plates exist in the large columns used in oil refineries. These columns are physically divided into sections by partitions or plates, and the material to be separated is alternately vaporized and condensed.
In chemical laboratories, the typical column is a glass tube in which the vaporization-condensation cycles occur on the inner surface. To increase the surface area, and therefore increase the number of theoretical plates, the column may be packed with glass beads, glass coils, or a stainless steel sponge. The efficiency of the fractionating column depends on the surface area of the column. The term usually used to describe the efficiency is the height or length of the column equivalent to one theoretical plate. Most columns in the laboratory are equivalent to several theoretical plates, although very efficient columns can be constructed which are equivalent to about 20 theoretical plates. The more theoretical plates in a column, the smaller the boiling point differences of the compounds that can be separated. A column with 10 theoretical plates can separate liquids with boiling point differences of about 25 degrees. If packing material is used to obtain these additional theoretical plates, it will physically retain some of the sample that is being distilled. This amount of liquid that must be present in the column in order to coat the packing material is called the holdup. Columns that contain packing material have a high holdup. Fractional distillations are performed routinely in the laboratory with apparatus that is commonly available. The flask selected for the distillation should have a round bottom or pear shape and be of such size that the material to be distilled fills it between 1/2 and 2/3 full. These flasks have several advantages over flasks with flat bottoms. First, the material will be heated in a uniform manner and the possibility of localized heating is reduced. Second, as the material is boiled away, the material that is left will be concentrated at the bottom of the flask and not spread out over a large surface area. The flask is clamped to a stand and sometimes supported by an iron ring or a heating mantle. The liquid to be distilled is placed in the flask and a few boiling chips made of porous inert material are added. These chips provide a large surface area where boiling can be started. This helps to prevent the possibility of the liquid superheating and subsequently boiling erratically or bumping. Very often, glassware with standard taper ground glass joints is used in the organic laboratory. Because of the precision required to manufacture this uniformly sized equipment, it is very expensive. Care must be taken at all times when using this glassware. At this point, a distillation column is placed into the flask. Although many types of columns can be used, the setup is similar to the procedure shown here with this insulated column. Columns are almost always insulated to ensure equilibrium is maintained throughout the column during the distillation and to minimize heat losses. After the column is inserted, it is loosely clamped in place. Depending on the conditions of the experiment, it may be necessary to grease the joints before the glassware is assembled. This grease provides a tighter seal for the joint. However, there is a risk of contaminating the reactants or products when grease is used in the joints. If you are instructed to grease the joints on your glassware, a very light film should be applied evenly over the full ground glass surface. A Y-shaped distillation head is placed in the column with a smaller opening directly above the column. This head serves two purposes. It connects the column to the condenser and also holds a thermometer in the vapors which will rise from the flask during the distillation. The boiling point of the material that is distilling can thus be observed. Next, the condenser is attached to the distillation head and clamped loosely to another support stand. The condenser should rest on the bottom of the clamp so that the clamp can be tightened from the top when the final adjustments are made. An adapter is used to lead the condensed material to a collection vessel. This adapter is also loosely clamped during the initial setup of the apparatus. All the equipment must be secured tightly before the distillation. However, the equipment must be aligned first to prevent stress on the joints, which may result in leaks or broken apparatus. To align the apparatus, first view the setup end-on to make sure that all the equipment is in a vertical plane. Straighten any twists. Then carefully tighten the clamps a little at a time in succession. Some small pieces of glassware, such as this collection vessel, have hooks and can be attached to the adapter by rubber bands or springs. When the equipment has been aligned and tightened, an adapter is placed at the top of the distillation head and the thermometer carefully placed in it. The top of the bulb of the thermometer should be set even with the bottom of the side arm opening of the head. In this way, the heated vapors which will form during the distillation will pass over the thermometer bulb. If the bulb is placed too high, the vapors will not reach it, and the observed boiling point will be too low. If it is placed too low, the correct boiling point of the collected distillate may not be obtained. A heat source is then placed under the round bottom flask. Several sources may be used depending on the equipment available and the expected boiling point of the distillate. Commonly used heat sources include a heat lamp, a heating mantle, a water bath, an oil bath, or a steam bath. Water passes through the condenser in order to cool the vapors as they come over during the distillation. Flexible tubing is connected from the lower end of the condenser to a water source, and a second length of tubing is connected from the upper end of the condenser to a drain. The water must flow into the lower end of the jacket of the condenser to ensure proper cooling of the distillate vapors. The water should flow through the condenser continuously, but slowly. If the water flows too fast, it puts too much pressure on the tubing and connections, and they may come apart during the distillation. After the apparatus is put together, the water flow is slowly started through the condenser. It is always wise to check the assembly carefully before beginning the distillation. Check that the top of the thermometer bulb is properly placed in the distillation head. The assembly is clamped, supported, and properly aligned in a vertical plane. None of the connections have opened during the tightening process. Boiling chips have been placed in the flask. The adapter is open to the atmosphere so that pressure will not build up during the distillation. And finally, that the water is running through the condenser jacket. Once all of these items have been checked, the heat source can now be turned on. Because a distillation must be monitored, it should be continually watched and never left unattended. Fractional distillation requires that the system be warmed slowly. Slow warming helps to establish the liquid-vapor equilibrium that is essential for a successful separation. Any attempt to carry out a fractional distillation too rapidly will result in a loss of efficiency. As the liquid begins to boil, the hot vapors rise up the sides of the flask and into the column. As they reach the cooler portions of the apparatus, the vapors condense and return to the flask. They also heat up the column so that the next portion of vapors rises higher than the preceding portion. Eventually, all of the apparatus is warm. There is a sudden rise in the temperature shown by the thermometer reading when the hot vapors reach the thermometer bulb. As the hot vapors of the distillate move through the water-cooled condenser, they liquefy. The distillate runs through the adapter into the collection vessel. The temperature observed when the first drop of the distillate is collected is recorded as the beginning of the temperature range for the fraction being collected. Distillate should continue to come over at a fairly constant temperature. After most of the lowest boiling component has been collected, the distillation rate may decrease, and the temperature at the distillation head may drop. The highest temperature reached before it drops is recorded. This temperature is the top of the boiling point range for the fraction collected. If the temperature does not drop, the highest temperature reached before the fraction is removed is recorded. In order to obtain the higher boiling components, if the temperature drops, the heat applied to the distilling flask should be increased. An intermediate fraction is collected until the boiling point of the next component is obtained. This procedure is repeated until all the fractions are collected. If the distillation needs to be stopped at any time, this is accomplished by either turning off or removing the heat source. However, the distillation must be stopped before the distilling flask is heated to dryness. If the flask is heated to dryness, it may break. Also, the residues remaining in the bottom of the flask often decompose or may be explosive. Thus, it is important to leave a small amount of liquid in the distilling flask. Once the fractions have been collected and the boiling points established and recorded, the fractional distillation is complete. The early distillation processes in industry were inefficient because fractionating columns were not used. No sharp separations of distillate products could be obtained. As demands grew for purer products, the redistillation of mixtures led to the use of columns. Today, fractional distillation is the primary refinery process.